Hello, everyone. Welcome back to M Plus Paper Club. Today we are going to speak about a very new, very fresh paper. Actually, now it's 3 weeks old, but it already made a bit of noise in Twitter and in the ML world. So I wanted to speak about it. It's a fairly non-technical paper, even though the work is very technical. In a funny way, there are no formulas at all. Uh, but they do cover quite a few useful, novel ML techniques for mostly for fine-tuning LLMs with larger context. Also, it's about training together with training text with images and videos. It's about multimodal training, so that's also very interesting. So let's begin. The title is Word Model on Medium Length Video on Language with Ring Attention. So clearly they are using RingAttention. We'll speak about this, but also a few other techniques to make the training more efficient. And as I said, they call it world model because it's a combination. The training data is a combination of books, videos, and images. Okay, and the million length part is about uh, the context window, which becomes 1 million for the largest 1 million tokens for the largest models. Okay. Can you see the screen here? Is this zoomed enough? So the abstract basically talks about abstract. Uh, let's actually skip that part. I like how there is a nice table of contents with subsections. Yes, Arvid.
Sorry, never mind.
Okay. Uh, so let's actually go down to a few examples because basically they're benchmarks. So this is a fully open source work. They provide all the details that the data sets are open source. Models, I haven't actually checked, but they claim it's all open source, um, which is great. But the best part is that the benchmarks are Gemini and GPT-4, right? So the top paid for models. So that's very ambitious. Usually those closed models outperform the open models, but here they go for the top benchmarks. And the first example here is about they give a video, a long video, 1 hour long, and ask a question. So the video is actually funny because it's a compilation of very diverse short clips, right? So that because this is challenging because normally if you have a long video, uh, the common practice is to subsample. So even if you have a 1 hour long video, you might end up with 8 frames subsampled from it, which means unless the video is relatively static, your model is not won't be able to capture enough information, right? Here, because they are able to scale the token size, the context window size, they are able to capture those details. And other experiments will also be of relevant, of similar nature, things like needle in a haystack kind of questions. Okay, so here they give a video, a long video compilation of various short videos from YouTube uh, to GPT-4V, Gemini Pro Vision. The Lava is an open source model, and their version. They call it LWM. Okay? And that's the question. I ask questions about it. And here are a couple of examples how all the other models fail. They either refuse to give an answer or they just give wrong answers, right? And their model is able to answer those questions. So that's the main advantage of long context. Okay. Um, let's scroll down to look at the introduction a little bit. Um, they actually highlight a few. Actually, let's go to the abstract because as I said, uh, learning from a million tokens is hard for a number of challenges like memory requirements, computational complexity. As we know, attention is even with all the optimized versions, it's still quadratic complexity, but also limited data sets. There isn't that much good data to train models for long contexts, right? And they address all these problems using ring attention. We'll speak about this in a moment. But uh, they also do this fun technique when they don't just use long context, but they start with short context and gradually increase the context size. The idea is that they first allow the model to learn short context, but then over more epochs, or over later epochs, they also allow the model to learn a longer context. This is just more efficient than always using long context, right? Simple technique that works very, very well. Yeah. Um, and they also highlight the main contributions for the paper. It's all in the abstract. Number one, the largest context size neural network. So they claim this is the largest context size uh, anywhere in any model. As we will see, when we get to very large context, all models fail. Right? All current art fails. Um, they also have a solution for vision language training challenges. Things like, because when you combine um, vision tasks with text tasks, things become challenging. Right? We'll go into details about what they do about that, like adjusting the loss weights, adjusting the masking, and so on. What is the technique referred to? Oh, there's a question. Let me read it out. Uh, what is the technique referred to in the literature? Suppose you.
It's not even it's not really considered like there's not a paper on this technique, but there's a lot of art literature in RL
Mm,
about training models, training agents to accomplish tasks where they have to perform a very large number of steps. And usually, what they do is they'll take, like, say your goal, you want to have the model of the agent accomplish a task that takes 1,000 steps. They'll put the agent like 100 steps away from the goal, and then they'll train it to do that. And then they'll put it 200 steps away from the goal, and they'll train it to do that. So, like, increasing the difficulty over time. And usually you see it as a description of the techniques used in experiments, as opposed to like in the method itself. It's just, they're like, when we were training these agents, we did this. Yeah.
thanks, Peter. Um, right. The other contribution uh, is the optimized implementation of ring attention, which allows to scale to very large context sizes. They also combine ring attention with flash attention to make the implementation very, very efficient. And as I said, this is all made public. It's a 7B parameter model also, by the way. The state-of-the-art comparisons are much larger models. Right? This is a 7B parameter model. It's actually Llama 7B fine-tuned. Uh, Also, I found it very useful reading through the technical details of how they fine-tuned Llama 7B, because if you fine-tune with other purposes, it's actually useful to understand what they do, how they make fine-tuning work better, right? How they curate the data set, things like that. Okay. Any other comments? That's the high-level introduction for the paper. Let's go into more details. Right, ring attention. Let's talk about ring attention. So basically, it's a way to parallelize attention calculations sequentially. Sequentially meaning that you. So the main problem with attention is the limited context window uh, because of memory requirements. Now, ring attention is a technique, a very recent one, that allows calculating like batched attentions over multiple GPUs. In this case, those are TPUs, uh, and then combining them. So in theory, this, because you can then come back to the original to the first GPU, uh, which in theory allows you doing infinitely large context windows. This is the main thing that allows this paper to reach 1 million context window. Okay. Um, so there is a citation for ring attention. Maybe we'll do a paper on that eventually. But for now, that's the main idea. Okay. Um, they also, interesting. This part is interesting because they said there is a lack of long form chat data sets. So instead, they use an LLM to generate chat conversations, which kind of backfires eventually because at the end they say, oh, actually, the chat quality isn't great, which is why our model can't outperform some of the state of the art on some tasks. So having better data sets would help. But if there is no data, what do? You generate that, right? So that was interesting. Um, they also said that they have to do a few adjustments uh, for uh, to combine training text, video, and images together. Okay, we've got to talk about this now actually. Um, so the training is done in multiple stages. This image actually captures that. Okay, so there is stage one when we extend the context to be the context for LLM. The stage two is the vision language training. Okay, so first we need to extend the context for the LLM. So they take the 7B Llama, which I think has 8K context by default, and then they gradually increase that. If you go down, you can see the context starts from 32K, and then it goes 128, 500. So this exponentially grows to 1 million. Okay, and as we increase the context size, uh, we also add more modalities. So the shortest context allows having images, right? Because the context is here is small, so we can fit images here. I will talk about the images also, by the way. And then we can add short videos, and then more videos, and then more videos, and so on. Okay, so the training data changes as we increase the context. Uh, Now, as we increase the context, we also have to adjust the ring attention. There is a theta parameter, which they say you can literally just linearly increase that. We will see it in the tables. There is a theta that defines uh, the ring attention. It's a parameter for the ring attention, and then they just increase that to adjust with the longer context. Okay? I also want to, before we continue, I also want to talk about the image embeddings, right? Because normally for image text models, we would see a clip embeddings, which is which are I think they covered that also during Paper Club. Clip embeddings are basic clip or blip. There is another version, and the idea is that you train image with a caption, embedding both of them into the same embedding space, right? And then you can use those embeddings. Yes, Peter.
Actually, I think that was considered state of the art, or may still be considered, but Gerard presented a paper where instead of doing any kind of like pre-training to get clip embeddings, they just take like images and they embed the text related to them, and they train the model to like uh, to output the text embedding, like an embedding that's close to the text embedding.
Mm.
So like they just freeze the language model, get the embedding for the text, and then say like, okay, minimize the distance between the embedding outputted by the model, the image encoder, and the LLM's embedding.
How do they embed the image then?
They just put it through the image encoder after it's been trained to do that.
Oh, I mean, how do you tokenize the image? Because it may be the same technique used here. Because you need
Uh,
to tokenize the image somehow, right?
well, no, because you don't, because you just put it straight into embedding space. You don't have to tokenize it, right? So you just need an embedding for the image that you can put into the transformer. So they just feed it into the image encoder, and then it outputs a vector, which is the same size as like a token embedding.
Okay, so that's um, so you train first the language model, and then you find the embedding for the text.
You just take a pre-trained. They just took a pre-trained language model, and then they train an image embedder. They take the pre-trained language model and use the embeddings as like the ground truth for the text, and use that as a target for the image embedder.
Okay, yeah, that makes sense. What I was trying to say here is they don't actually embed the images. What they use is this binary vector, no, quantized vector GAN model, which kind of serves like a tokenizer for the images, because the quantized vector. So you run your GAN, which means you can't actually give a prompt, right? But then because they use this discrete quantization for the I guess embeddings from the images that GAN produces, you end up with a sort of a tokenized version, which means those images have not seen any text before, right? So there is no text image pre-training of any sort. Uh, uh, I so they say that it's a funny thing, because they choose to do that, and then they say for some tasks they can't compete with state of the art because state of the art uses clip or versions of that. Because like whatever the embedding method we use, the idea is that normally image embeddings would be aligned with the text embeddings, right? But here they are not aligned, because with GAN you can't do prompts, right? So you basically just continue training. Yeah. Thanks, Peter. Okay. So here, I think it's the overview of the approach. Any other comments here? Okay, let's scroll down. Okay, so here we have the model architecture. So VQ GAN is the vector context I mentioned, which so image goes through that model, and then we get image tokens. So this VQ GAN serves as like a tokenizer, and then we have the LLM, the autoregressive transformer, because they also say that this way we can do the training autoregressively, which you can't really do if you have an image text embedding. And then you can predict the next image tokens. Okay. So that's the process with images. Let me see if I missed anything here, because the image the figures in this paper are kind of scattered across the text, so they don't really align with the text. So I want to make sure I don't skip important text here. Right, as I said, they make a combination of ring attention and flash attention, and with a very efficient implementation. I don't actually know what's Palace. I didn't check this one. Probably a more efficient implementation of attentions, I suppose. All right, we mentioned about progressive training on increasing context length, right? That's we did. Positional extrapolation for long context, right? I mentioned that this theta parameter for ROP is the positioning encodings. I think we did ROP. So here the idea is that we use complex numbers to represent positioning encodings, which gives us actually two values for the positioning encoding, and then we extend theta, which is the parameter for raw positioning encodings. And just by doing that, we are able to extrapolate the positioning encodings for long contexts. So we have to adjust that too, right? We can actually look at that. There is a table with those values. So you can see that there is a table with different context sizes. It's the same 7B parameters, right? The model doesn't actually get larger. Sequence length increases exponentially, by the powers get larger as the context gets larger. The theta for ROP also increases. This is basically discovered by experimentation, how to increase theta. The tokens per batch remains the same, very large number of tokens because they are using very powerful TPUs. I think they said this is equivalent of 450 A100s. These TPUs are very powerful and expensive, obviously. But the paper is written by
How? Like, how did they get so much compute? Like,
Berkeley has a lot of compute power. The paper is written from Berkeley, University of Berkeley. I
but
think
Google doesn't sell TPUs, do they?
they do. We have access to TPUs also. You can't buy a TPU for your data center, but you can access it. You can pay for it on Google Cloud.
I
but
think
they're very expensive.
Sorry, I think Google have programs where they will allocate research. Basically they'll give research grants in the form of access to GPUs and TPUs. So I think that's probably what's going on here.
Yep, I agree. Probably research grants. But anyway, it's good compute. And they are actually able to train. They have the workload times here. This is just text chat training per part. No video here. So the largest ones would take 40 hours to train, which is not that bad, right? It's fairly fast because it's only fine tuning 7B models, right? With larger context, but the model itself is not the largest kind, which I like. It's great to see that medium-sized models become more popular. Okay, let's go back. Training steps. Right, we spoke about those. Okay, chart fine-tuning for long context learning. So we have a few details here about constructing question-answer data. And then they chunk the data from books. So books is a data set from books. But then they actually mix the chart with books data. I think we have details later. But there is fine-tuning on chart data set also, chart data also, because otherwise model won't be able to answer questions to, I won't be able to answer questions as a chat. You need to fine-tune on chat also. Some more training details here. Yeah, as I said, they take a few data sets, combine them. The 7:3 ratio, again, probably experimentation. But I like how they give all these details. I think that's all interesting things here. Now, before we continue training with video, they do an experiment on text model only. So that's the needle retrieval, right? So you have these are actually artificial data set data, where basically you have random data and then there is one specific information that you want the model to find, right? Which means unless your model is able to attend everything in the data, it won't be able to find the needle. And the experiments, let me find the experiments. All right, here. So first of all, they show that their model basically gets almost perfect accuracy over all context lengths. This is accuracy 1, basically, which is great, right? You can actually have a very large haystack, and then you will find the needle. But this is only if you have a single needle. Things get worse when they introduce multiple needles. So these experiments show there are like 4 needles. You need to find 2 of them at the same time. So here it gets harder. If you have 4 and then find only 1, it still performs pretty well. Longer context kind of gets a bit worse, but it's still good. But when you introduce multiple needles and you have to find multiple of them, even two, right? Performance degrades a lot. So there's the limitation for the model, and you can also see it when comparing against GPT-4 and Gemini. Again, when we have multiple needles to find, like the first and last row columns here, you can see that the model starts struggling. Except when the context is 1 million, the other models can't do anything anyway. Right? So Gemini and GPT-4 just can't extend to 1 million contexts, at least when the experiments will run. I think now they can, right? The new versions get to 1 million contexts actually. At least Claude does. So LLMs aren't good at multitasking. Well, yes, this is a very hard problem. There's a comment that maybe LLMs aren't good at multitasking. Well, sort of, yes. But this is, again, a very hard problem. Also, if you look at here, right, even if you have multiple R's, GPT-4 is very good when the context isn't too large. So that's not too big of a problem until we get to 1 million context. Okay. Any other comments? Yeah. I think Gemini 1 Pro is supposed to have one. Yeah, exactly. So here, this one is Gemini 1. This is 1 Pro. Julian?
I mean, I understand what this particular eval set is for, which is like for testing for the long context, but it's a really artificial kind of eval because you're asking the model to find some random, completely sort of, so you're asking it to find like a known sequitur in the middle of a giant piece of text. So there's probably quite a lot of signal just in the fact that it's a very kind of a piece of text that's been parachuted in, like a sentence that's been parachuted into this text that is really a known sequitur. And that might also explain a bit why it is a lot harder when there's multiple needles, because when there's only one needle, you can use a lot the signal where it's like, oh, this is a piece of text that really doesn't fit. But when there's more than one, that's not going to tell you right which one.
Yeah, I agree. It's a hard task. It's an artificial task. But these days, this is one of the common tests. Even with, again, new Claude, right? There was this tweet how they also test models internally with these sort of tasks. So you would give a random text and then one sentence that stands out, and then you ask it to find it, or actually all completely random text, and then ask to find one sentence that exists there. It's a very hard search, but it's a common test, right? Like to understand the limits of the models. So what is more interesting is to find something in a long talk that is congruent with the overall. Yes, yes. Oh, they also do this experiment that, and then again, this model is a little limited in terms of understanding the higher level overall concept of when the sequence is very long. We'll see those experiments also. But I agree, that's a more useful thing to do. Yeah. Cool. I think we can scroll down here. Oh, here they basically just compare this model's performance on the baseline Llama 27B on standard tasks and metrics, just to evaluate that the performance doesn't change much. So this model can still do what Llama 7B can do. It's like a sanity check. And then chart evaluations. I didn't fully understand this part, but the empty bench. It's a benchmark, empty, but I'm not sure what exactly it is. It says here, it's a common benchmark, blah blah. Up here, thousand performance on empty bench scores. I'm not entirely sure what empty bench is. We additionally evaluated our model on empty bench. It's some benchmark task, right? I'm not sure what's special about that. What we notice is that when we train, well, the larger model perform a little worse on this empty bench benchmark. But also, I think it's a chart data set. benchmark for chat questions. Actually, it's a chat data set. And then they also evaluate, like, when you train, the mix between chat and QA data. So it's a more of an ablation study, right? As you go from more QA into more chat, you can see that the performances go the opposite direction, right? Empty bench gets better with more chat, but then the needle accuracy gets worse. You can't have both really, unless you find something in the middle that's good enough for both. I think this is what they used actually, right? So they just show that there is a trade-off between those two tasks. If you want your model to be better at chat, it may not be good at finding the needle. Okay. We talk about vision language models. So the original model they call LWM, large world model, and then large world model chat. But now they also have the vision version. So this vision version is, let me go down. Here's an example of how it's used. Right? You would give a video, and then what is the video about? You would get a description, right? And then you would ask a question. What assistant answers question about a film? Well, wait, yeah. What is the if you ask this later, um, you basically can answer questions about different parts of the video, like an example of that. But I wanted to show something different. I can't find it now. Oh, here. Maybe this was it. All right. So it can generate images and videos from text. I didn't actually see the actual long videos because they put them in the appendix as more examples for images or videos. I can't see the actual. Well, obviously they can't put videos here. That's a little tricky. But they claim they can generate videos. Okay, let's go up. Architecture for vision, right? Architecture for vision. That's important. So they use this, as I said, VQ gun to generate, to create, to tokenize video and images. They also introduced these special tokens. This is quite standard to distinguish between text, image, and video. Right, so you would have these special tokens to make sure that things are tokenized correctly, right? Because you don't want to mix and match text tokens and video tokens. You want them separated. But the training is done together. It's all trained together as a second stage of fine tuning. Okay, and again, the context size increases, right? So we have the 1K, 8K, and then it goes up to million. Right? So we get the larger context for the last stages only. Initially, as I showed before, remember, initially there was no video for shorter context. And they also have to do this packing thing because we have different context sizes, right? We need to pack this efficiently, deal with masking, and adjust the weights, because for video and text, loss functions are different. So we need to actually weight the losses from different parts. Otherwise, training deteriorates. They do have an ablation study later about that somewhere down here. I think that's the one. If you don't do the packing correctly, performance actually on all data, on all benchmarks actually degrades. So this is important to weight the losses, the loss functions. A few more experiments. Let's see what we have here. Large video, the evaluation of the results for video, video understanding. Let's look at the tables. So those are different data sets. And then every other state of the art here uses clip, but again, maybe those are kind of old. Maybe half a year ago, or maybe a few months ago, it was clip. Nowadays, as Peter said, there are better ways of embedding. But the idea is that even these newer ways of embedding would still have text and image embeddings trained together or fine-tuned together at some point. Right? Here, what they do is they use this VQ GAN, which is only images. It hasn't seen text before. And then the text image training happens as part of training for this model, which is why performance here can sometimes be worse than state of the art. Like this one is so much worse than the rest. Everything else is usually like okay-ish, right? But they do claim that for longer context, none of the previous models can actually deal with it. What I don't understand is that why do they choose to use GAN, right? Um, there is one comment at the end when they explain that part. Let me find that comment. One moment. I think it's back here. Well, they do say that improving tokenization would be useful. Oh yeah, here. However, there is clip or similar clip or blip embeddings. They can only be trained on to predict text given visual input, but not vice versa. So for training, you cannot use these pre-trained embeddings um, to predict visual, to predict images given text. Right, so training is done the other way around. I think that's why they choose to use the GAN tokenizer, because they also do because they train everything together. It makes more sense for this architecture. Okay. A few more plots about training. Because here they actually show how much energy they spend. Again, larger models become less efficient. So this is the utilization, model flow utilization. So higher is better. And they also have the training times, which can take, I think the largest it was 10 days. So it's not as bad as training an LLM from scratch. I think that's all. Oh, training curves here. Nothing too interesting. This, I guess, worth mentioning. So this is the loss function over training time over days, like 6 days is the most they get. These spikes is because of the introduction of new tokens. There is a little spike because there is a new token, and then it starts going down. But there isn't much else interesting. Related work, we mentioned. I think we covered everything. Rope position and embeddings, instruction tuning, also combining vision and language. This is where we spoke about clip. I think that's all. Okay. Any questions? Any comments? They won't go too fast with the videos.
Why is it called world model?
Because it's a combination of video, images, and books. And the argument is that if you don't include video, your model won't be able to learn temporal behaviors. With an image, you can't really do that. They do mention that adding audio or other sequence data for future work would be useful. But they call it world model because it's video and video, image, and text. Books, really.
This is all making me wonder if, like, in the future, we'll like only use transformers and we'll just be able to embed every single data modality into transformers. And
or selective state space models.
Yeah, maybe.
Yeah.
But I was just thinking, I wonder if there is something we're still missing for making these models more data efficient. Because like that's probably the argument for transformers.
Yeah, this is the well, computational complexity, right? Yeah, yes, I agree. It's Mamba or state space models. They are catching up very quickly because of efficiency problems with transformers. Yes, Damien.
Just going to say that regarding the data efficiency, there's also these models with reduced precision where they've been trained with like less than 2 bits of information per weight, which is probably where this is heading as well.
You mean quantize the weights to be more data efficient?
Yeah, it's like this recent paper that proposed 1.58 bits per, I think, per weight, and that was catching up to like state-of-the-art results.
Because video has temporal information, but it also has a lot of unnecessary information. There is a lot of redundancy in video also. So maybe there is scope to improve to improve performance there.
True. Maybe like I wonder if you could train a model on compressed video, on compressed images.
Yeah. Didn't we have a paper about training on binary data 2 months ago? I think we had a paper about training on binary data. Yeah. We did consider presenting the Microsoft paper with the 2-bit quantization, 1-bit quantization. However, it was a bit too short. Maybe we should do that anyway. Or maybe if they release more details, we can do that. Any other comments? Okay, thanks all. So important thing, next week, yeah, thanks, Julian. There's the paper. So next week, Paper Club will be in person. It's a special event. It's in the evening, actually. It's hosted. It's hosted by what's the company called actually? Hyperstack, and Peter is presenting in their offices. There will be food. Also, we are also part of Alan Turing Institute's event. So it's like all together. We'll probably have a larger event than usual. So all welcome to join us there. And Peter will do more of a presentation combining a few papers about aligning LLMs. Okay. Yes, next week's event is now on Meetup. Please sign up so we know how many people are coming. Spaces are limited, but we should be okay. So looking forward to seeing you all next week. Thanks.
Thank you.